In this module, we will discuss the temperature dependence of the rate constant. Previously, we have noted that the rate law, which is a function representing the reaction rate, can be expressed as a product of two distinct functions. The first quantity in this equation, K, is known as the rate constant of the reaction. The rate constants are influenced primarily by two parameters, temperature and pressure. A key observation in chemical kinetics is that chemical reactions generally accelerate as the temperature increases. This phenomenon is predominantly due to the variation of the rate constant with temperature. As the temperature rises, the rate constant typically increases, leading to a faster reaction rate. A rule of thumb describing the temperature dependence of reaction rates is the Van 't Hoff's rule. This rule states that for every 10 Kelvin increase in temperature, the speed of a chemical reaction increases by a factor of 2 to 4. It is found experimentally for many reactions that a plot of the natural logarithm of the rate constant, ln K, against the inverse of the temperature, 1 over T, exhibit a linear relationship. Based on the data known at the time, Svante Arrhenius proposed in 1889 the following expression for the rate constant, known as the Arrhenius equation. K is equal to K0 times the exponent of the negative of EA divided by RT. Here, K is the rate constant, K0 represents the pre-exponential factor, EA is the activation energy of the reaction, R is the universal gas constant, and T is the temperature. In the Arrhenius equation, the pre-exponential factor, denoted as K0 or A, signifies the frequency of molecular collisions with a correct orientation of reactants that is necessary for a reaction. It reflects both the collision frequency and the probability of reactants having the correct orientations, which is crucial for initiating the reaction. The activation energy, denoted as EA, represents the minimum energy required for a chemical reaction to proceed. Together, the pre-exponential factor and the activation energy are called the Arrhenius parameters of a reaction. The Arrhenius equation can be interpreted as stating that the reaction rate equals to the product of two factors. The first is the frequency at which the energy barrier to reaction is approached. It is given by the pre-exponential factor. The second is the probability that the reactant or reactants have enough energy to cross over the energy barrier. It is represented by the exponent term containing the activation energy. Together, these two terms describe how often a chemical reaction is accomplished. The dimensions and units of the pre-exponential factor are the same as for the corresponding rate constant. As we had discussed before, they vary depending on the reaction's order. The dimension of the activation energy is energy per amount of substance. The corresponding coherent SI unit is joule per mole, although the activation energy is typically expressed in kilojoule per mole. Taking the natural logarithm of the Arrhenius equation, we obtain the following relationship. This equation represents a linearized version of Arrhenius equation. It suggests that plotting of the natural logarithm of the rate constant against the inverse of the temperature will produce a straight line. A graphical representation of this type is known as an Arrhenius plot. By plotting experimental data on temperature dependence of a rate constant as an Arrhenius plot, one should obtain a straight line. The slope of this line equals negative of EA over R and allows to determine the activation energy. The intercept at 1 over T equals 0, corresponding to infinite temperature, provides the pre-exponential factor. From the Arrhenius plot, where the slope is proportional to the activation energy, we can draw several conclusions. The higher the activation energy, the stronger is the temperature dependence of the rate constant. If the activation energy is 0, it means that the rate constant does not vary with temperature. A negative activation energy indicates an unusual scenario where the rate constant decreases as the temperature increases. In our discussion of the temperature dependence of reaction rates, it is important to acknowledge the limitations of the Arrhenius equation. First, its application is limited to a specific temperature range. Therefore, when using this equation, one should be cautious, especially when extrapolating rate constants to temperatures outside the studied range. Second, the Arrhenius equation is largely empirical and may not always accurately describe the temperature dependence of the rate constant, particularly for complex reactions. For many reactions, Arrhenius plot does not yield a straight line. This indicates the temperature dependence of one or both Arrhenius parameters. For example, the activation energy can be temperature dependent and be considered as a formal parameter indicating the rate constant's sensitivity to temperature changes rather than modeling an energy barrier. There are other, much more advanced theories that describe the reaction mechanisms and temperature dependence of reaction rate constants. Nevertheless, although the limitations of the Arrhenius equation are well known, this relationship still provides an adequate description of the temperature dependence of reaction rate constants for a wide variety of reactions.